the last class?
So just started the dynamic.
We had introduced the dynamic logic. So what is dynamic logic? Why is it called so?
So because the output is not driven and like always driven, and we get a floating kind of output, and it depends upon the charge that is stored on the capacitor. So not always driven.
So while in static gates, we say that the output or all the nodes are always driven. You do not leave things non-floating in static CMOS case. In dynamic logic, we realize that there is only N stack, and on the PMOS side, you have a clock-based header, and at the end of the bottom of the NMOS stack, you have a clock-based footer. And you said that this system will lead to a floating gate condition when the remaining NMOS stack is off. The PMOS will go off when clock goes high, and you will end up having floating output. So since that kind of, and then at that point of time, you are dependent on the charge stored on that floating output to ensure that you are stable, that you are robust. So that is where it is called as a dynamic. Due to leakage, you may need to refresh this. So at the end of every clock cycle, this capacitor, whether it had discharged or not, will again be charged up to VDD. Okay, so we also started to look at the challenges or limitations around dynamic gates. What were they?
Sir, there is very less noise immunity.
There is very less noise immunity. Okay.
For a particular, within a single cycle of the clock, the inputs can be changed at most once.
So the inputs can change only at most once. An input can go from 0 to 1 only once. If there is a glitch, then I have a problem. Okay. What else?
To charge and discharge this, the power consumption is high, sir.
Activity factor is very high. So
yes, activity factor is also very, that's something different, but yeah.
Yes, activity factor is very high because in terms of when you compare it with a static gate, even if the inputs have not toggled, a static gate would not consume any power, but a dynamic gate will always consume power. Because at the end of every evaluation phase, there is a pre-charge phase, and in that pre-charge phase, whatever capacitances you had discharged would get pre-charged all over again. Okay. What else? So we also saw that in dynamic gates, the total number of transistors would be something like N plus 2 versus 2N for the static CMOS. You're able to see this N plus 2, the plus 2 things?
yes, sir.
The header clock, the PMOS with the header clock, and the NMOS with the footer clock. Then the good thing about this is, so we have lesser number of transistors, but much better situation than let us say PTL or pseudo NMOS, because outputs are full swing. Outputs are full swing. The output is either full VDD, and when it has to be 0, it will be taken to full ground. So outputs are full swing. And because outputs are full swing and the NMOS stack or PMOS stack is not, there is no race condition or fight back between the two NMOS and PMOS stack, like in pseudo NMOS kind of a case, the sizing does not really affect the logic levels. The sizing affects the delays, but it does not affect the logic levels. And what also has happened, we discussed this also in the last class. We've reduced the capacitance. Which all capacitances have we reduced?
Input.
All the PMOS.
All the PMOS one.
The PMOS.
So we reduce the input capacitances because there is no PMOS. The signals now no longer need to go to the PMOS. So if I would make a inverter, a dynamic inverter, the PMOS would have a clock on it. There would be one NMOS with a clock on it, and then there will be the other NMOS. So the effective logical effort of this dynamic inverter would be, can you quickly tell me? Hello?
So 1/3.
1/3. So wait a minute. I seem to have lost control over my PowerPoint slideshow. Why 1/3? Just correct me. 1/3 कैसे?
Sir, it
There
is
are two
2/3,
NMOSes
sir.
in stack. There are two
2/3.
NMOSes in stack. How would you size the NMOSes?
2 for the input and 2 for the clock.
Two for the device, 2 for the input gate, and 2 for the clock. So what is the total load that the input gate is seeing now?
2 units.
2 NMOS, है ना? So what do we do then? What is this thing then?
The logical effort is 2/3, sir. Then
The logical effort is 2/3, है ना?
So do we still divide by the static
2 by
3?
3.
Yeah, we can divide by the static. Like that is the reference for us as of now, is it not?
Sir,
है ना? Yes.
so how it has become 2 by 3? Can you please explain that again?
What is the input load of a regular inverter?
So 3.
And what is the input load of this inverter that we talked about?
So we have a NMOS in between that will be of size 1.
Why?
So 1 ही होना चाहिए ना. अच्छा,
क्यों?
we have a footer 2. So उसका size 2 होगा, footer का भी 2 होगा.
है ना?
Yes sir. हाँ, okay. Understood sir.
So if you look at it, just give me a moment. Your system would look like this. Am I right?
Yes
This
sir.
will be a dynamic inverter. So the logical effort is 2 by 3. Okay. Fine.
Yes sir.
Okay. So then what do we do? If we say that this is the kind of logical effort that we have, what now logical effort se वापस आते हैं. What other constraints do you see would be happening with this kind of a dynamic gate now? You're circuit designers. So what kind of things would you see in the dynamic gate now?
So I mean, I can see that we cannot use like cascades, like stages in stage concept here, like dynamic.
Interesting. Why do you say so?
So because we have that constraint now, because that input can go from only 0 to 1. And suppose we have cascaded it. So if that is going, the 1 is going there. So in that, for the subsequent state, it will disrupt that. The same kind of problem we will face that we didn't want to face with this.
Same kind of problem, matlab?
So I mean, like if we have inputs other than going from 0 to 1, then we see that if the capacitor discharge, then we don't have any option. It will, and that logic then will basically, we will get different kind of, we will get basically wrong outputs basically.
But the dynamic will always have 1 to 0 transition at output. Right?
Yes, because at the end of the cycle, you had recharged it to 1.
1.
So if the output has to transition, it will always be from 1 to 0. There is no other transition possible. And it was already 1. It can only go to 0 now, or it will remain as 1. When it remains as 1, what do we say it is? Floating.
Yes, sir.
When it remains as 1, we say that it is floating. Are you with me? Because the PMOS is off. In the evaluation phase, CK equal to 1, so PMOS is off. And we say it is floating. And this PMOS on which CK goes will be off. Friends, I want feedback.
Yes, sir. Yes.
Yes, sir.
Okay. So once we look into this aspect, then we say that let me show my slides again. Just give me a moment. So then we come to other properties of dynamic gates where we say that overall power dissipation is higher. We do not want glitching to happen. And we already said higher transition probabilities, and clock has very high load. Are you able to see this? That in a static CMOS logic style, there is hardly any load on clock. Clock only goes to the flip-flops. Whereas over here, clock goes to every combinational gate. So the load on clock is very high. And we know that for clock, alpha is equal to, activity factor is equal to 1. So that is another reason why overall power of a dynamic logic system is very, very high. One is that there is all additional toggling on the inputs also, higher transition probabilities, but extra load on clock is also there. Then the pull down network starts to work as soon as the input signals exceed VTN. So the transition level VIM and VIH are equal to VTN. As soon as the input touches VTN, you now know that okay, my output is starting to discharge. So if there is a noise of more than VTN, your output starts to get corrupted. So we talked about low noise margin already. Precharge, okay, we already know. So one another important issue. So we talked about the floating output. So why is that an issue? That is an issue because see, there is this diode leakage over here. Due to this, what happens is that you wanted the output to remain 1, but it is floating. Due to this leakage, this output will discharge.
Yes, sir.
And this then needs to be restored. There is no way to restore this. So what you need to do otherwise is you need to give the next clock pulse. So clock goes to 0, then again it recharges back. So you need to give this refresh kind of a pulse over and over again. This also leads to extra power consumption.
Sir?
Yes.
Sir, I mean, like we can say that we can also reduce this period for this discharging is happening. Then also we can limit that then basically.
Yeah, but it is so okay. How is the clock period of a pipeline or any logic determined? It is based on that overall evaluation time of that combinational block, na?
Yes, sir.
So if you need some period, then you need that period.
Okay.
Are you able to see this?
So that is constrained.
It would depend upon the critical input as well, right? The input which is most delayed.
Yes. So there will be lots of signals which are coming to your combinational logic, and the last one, and how much time it takes to evaluate that one, that will finally determine how much you need. So how do we correct the charge leakage problem? By using something very similar to what we call as level restorer in the transmission gate or pass transistor logic. We call it a keeper over here. Okay. This transistor that we put as a half latch back there is called keeper. And now what you get is you get out bar at the output. Are you able to see this?
Sir, actually this keeper here will only prevent the charge from the CL to prevent the CL charge from discharging. But
it will recover any leakage that has happened from AB stack.
Yes, sir. So I mean, in effect, it is preventing the charge leaking from that load basically, or restoring that.
Charge does not leak from the capacitor, no?
Because now it will be from the directly from the VDD.
Charge does not leak from a capacitor. Charge leaks from A and B, the transistors or that have A and B connected to their gates.
Okay.
Capacitor थोड़ा ना leak कर रहा है. Capacitor
No,
का
yeah.
charge leak कर रहा है.
No, actually the charge is provided actually. I was taking that.
Yeah.
Yeah. So now, but ineffectively the power that was lost due to leakage that will lose, but now the source is different basically.
Yeah. So leakage you cannot reduce. You're not reducing leakage.
Okay.
Just saying that the impact of leakage on the gate and its reliability has been mitigated.
Okay.
Okay. Rajneesh, you have a question?
Sir, can you move back to one slide, sir?
Okay.
सर इसमें सर जैसे आपने बोला सर कि आउट जब ये ऊपर हम लोग का प्री चार्ज ऑफ रहेगा तो हम लोग का आउट ये लीक करता रहेगा इस रिवर्स डायोड की थ्रू। पर सब जब हम लोग ये प्री चार्ज भी ऑन कर रहे हैं तब भी तो सर ये डायोड रिवर्स बायस है सर, तो तब भी तो लीक होना चाहिए सर जब।
Yes, but then there's a stack effect also coming, na? CK is also 0. See, when this device is fully on, then anyway there is something that will provide charge to this node. I don't have a problem, na?
Yes.
Whatever leakage happens, that it will follow this path, not this path.
Okay, sir.
Are you able to see that?
Yes, sir.
Hai? Okay. So, anything
Sir,
else?
Sir, this inverter that I use will be static.
This inverter that I used, yeah, this will be static.
नहीं तो सर लूप बन जाएगा.
Yes, otherwise it becomes tricky. It will not. You cannot really cascade it like this. Tarun?
Sir, that out bar is meant only for keeper circuit, right? If I want to transfer the output to next stage, I will be using the out, the on one on the CL, right?
No, not necessary. In fact, we use the out. So as we talk about cascading gates, so there is a complexity in cascading the gates. Someone pointed that thing out. We'll talk about it in a little. So as we will talk about it, you will realize that we cannot have a gate or we cannot have input transitions going from 1 to 0 in a dynamic gate. See, we said only one transition is accepted. What is also important to realize is that that transition has to be a rising transition. It cannot be a falling transition. Are you able to see this?
Yes, sir.
So if it has to be a rising transition, then the output has to be inverted from whatever you got from the dynamic gate. So actually you will use out bar at all the places where you need to use this, the output of this combinational gate. Okay. Vaishnav?
Sir, yes, sir. So the inverter which I am placing after my position of my load, sir, that should be sized according to my keeper, right, sir? Or am I thinking of it something
Output
else?
load. That should be sized according to the load that you want to put on this.
Sir, but the output of my inverter is connected to my keeper, and I should make sure that my keeper works fine whenever my output, main output is going down. So in this sense, I think my keeper should be, my inverter should be sized according to the keeper.
Yes, it has to be sized according to the keeper and also on the load that you put on out bar. That is what I'm saying.
Okay.
The load that you put on out bar will be much, much larger than this keeper. This keeper is going to be very small. Just like we talked about level restorer in the PTL, this keeper has to be very small so that it does not fight back the input transitions.
Okay, sir. Sir, and one more small question, sir. So, sir, in project, we are supposed to place our load at this position only, input, before the inverter position, 25 femtofarad, which we were talking in the domino logic.
Yeah, I just answered this question, no? Not necessary. In fact, Tarun asked exactly this question. I said, no, you will have to put it on the output of the inverter.
Okay.
If you have static gates following it, then it can be different. But if you have dynamic gates following it, it has to be an out bar.
Okay, sir. Okay. So, okay, sir. Understood. Thank you.
Okay. Madhur?
Sir, this level restorer, you said that this level restorer has to be small, but we are keeping it so that it can reach, it can restore the level of CL. But if it is small, then it
Only
will have
leakage.
high.
Only leakage, no? So it's only leaking. The leakage currents are much smaller than on currents, is it not?
Yes, sir.
So you need a very small keeper.
Okay, so even small keeper will restore the charge even if it has a high resistance.
Yeah, because this keeper will be fully on. See, the keeper is on. Output is expected to be 0. Out bar is expected to be 0. So the keeper is fully on. And the PMOS is in saturation region.
Yes, sir. Okay.
So saturation current of the PMOS versus off current of the NMOS. So keeper can be fairly small.
It will still depend on the size. It's a saturation current.
Yes, but you will see, if you're working on the project with the dynamic gate, you will see the keeper will actually be very, very small. Not only will the width be 0.135, you will also keep length much larger than 0.06.
Okay, sir. And so one more thing is that in all these restorer circuits, we are actually creating a feedback. So wouldn't that feedback? I mean, how will we ensure that this feedback is we actually get out of this feedback whenever we
By
want?
keeping this keeper and level restorers very small. That's the purpose. If we keep these small, then even the regular strength NMOS will be able to fight back, no?
Okay, yeah.
That's the primary purpose.
Okay.
So see, the functionality is only to recover the leakage charge. So you don't need much current anyways. Then another constraint is you do not want it to fight back the forward path.
Yes, sir.
So you keep it small. Both the constraints lead you to keeping this keeper very, very small as possible.
Okay, sir.
Okay.
Yes, sir.
Yeah.
Sir.
Raghav.
Yes, sir. So with this keeper, you said that earlier in the dynamic side that it is a non-ratioed like logic. So to maintain that, then also like we had to keep the keeper like to be like 0.135. We cannot increase from that.
The keeper is, as Madhur also mentioned, keeper is a feedback.
Yes.
As soon as you have feedback, ratio logic comes in again.
Yes, sir. Yes, sir.
So until there was this no keeper there, everything was fully logical. As soon as we have this keeper, a sizing constraint comes in. The keeper has to be as small as possible.
Yes, sir. So, but you said that we will also increase the length, like to maintain that.
Yeah.
Okay.
Because if you cannot reduce the width less than 0.135 in your technology, and you want to still make it weaker, the easiest way is to increase the length.
Okay. So, but like my point was, I understand that we had to keep it to the minimum side, but what exactly will be that sweet spot? Like, how do I know about that? Okay, I cannot.
You check the leakage of your device.
Okay.
You check the leakage of your device at FF 125.
Okay.
In fact, you should do it at FS, fast NMOS, slow PMOS. At FS 125, highest voltage, the keeper should be able to, because PMOS is now slow, the PMOS keeper should still be able to compensate for the charge loss through the NMOSs, which are fast. Temperature is also high, so leakage is high.
So why shouldn't I prefer the FF 125, 132 and FS?
And you will make the keeper also fast. It will anyway be able to offer more current.
Okay, right. Yes.
For the worst case sizing, you have to test it at, you have to size the keeper at fast NMOS, slow PMOS, and at high temperatures and at high voltage. So that leakage is maximum, and at high voltages, at high temperatures, the drive strength of the PMOS would also reduce.
Yes, sir.
That is the pace where you will size the keeper.
Yes, sir.